Discovered by Benoit Mandelbrot around 1980, the Mandelbrot set that is shown in this image is one of the most recognizable fractal images. However, in order to understand the equation that generates this image, a new set of numbers is needed, and that set of numbers are called the complex numbers and are what we're going to talk about in this video. Let's begin by defining a complex number. In this image, we see that the complex numbers lie outside of the real numbers that we should be familiar with. The real numbers are the rational numbers, integers, whole numbers, and irrational numbers. The complex numbers lie outside of that and include the imaginary numbers. More specifically, complex numbers are written as the sum of a real number and an imaginary number, or z, which is the complex number, is equal to a plus bi. The real number a is called the real part of the number, and the real number b is called the imaginary part of the real number. That's because b is attached to I, which represents the imaginary number. What is I? Well, if you take I and you square it, that is equal to -1, or, square rooting both sides, I is equal to the square root of -1. Using imaginary numbers allows us to actually take square roots of negative numbers, and that's where they can come in really handy. Now let's look at an example where we perform some basic arithmetic operations on complex numbers. Suppose that we have the complex numbers z equals 1 minus 3i, and we also have the complex number w equals -3 plus 2i. And we want to perform the following operations. We want to find out what z plus w is, what z minus w is, and what z times w is. So let's begin with z plus w. I'm going to take and I'm going to use the complex number z, which is 1 minus 3i, and I'm going to add to that the complex number w, which is -3 plus 2i. Now, I can probably just look at this really quickly and see what parts are like terms, but I'm going to go ahead and write out all the steps. I'm going to rewrite 1 minus 3i as 1 plus -3i, and I'm going to add that to -3 plus 2i. Now, the parts that are the same, that are like terms, we've got real numbers, the 1 and the -3, so I'm going to go ahead and add those. That gets me, let's see, 1 plus -3 is -2. And then I also have the imaginary parts, which are -3i and 2i. Those are imaginary parts because they have that I connected to them. What is -3 plus 2? That is -1. So I'm going to write plus -1i, and I can leave it like that, or I could rewrite this as -2 minus I. We know that 1i and I are the same thing. All right, so that's what z plus w is. Now let's go to z minus w. So same thing, I'm going to have 1 minus 3i, but now I'm going to subtract -3 plus 2i. I want to make sure those parentheses are important because they're going to help remind us that we need to distribute this negative to both of those terms. Okay, so I'm going to rewrite this as 1 plus -3i, and now I'm going to distribute that negative. So if I distribute minus to a -3, that's going to turn into a +3. And if I distribute the minus to the 2i, I'm going to get minus 2i. Or maybe we want to rewrite that as, let's just write this as 1 plus -3i plus 3 plus -2i. You may or may not want to do that step where you change it from subtraction into adding the opposite. It can be really handy if you find that you're making some mistakes where the signs are off. All right, so now we've got 1 and we've got 3, and 1 plus 3 is 4, and then the imaginary parts, the -3i and the -2i, so we're going to call that plus, what is that, -5i. And we can leave it like that, or we can rewrite this as 4 minus 5i. And that is what z minus w is. All right, for part C, let me move into this bottom space here because it looks like I'm running out of room. So I'm going to say part C is z times w, and I'm going to take the complex number z and I'm going to multiply it by w, negative 3 plus 2i. So what we really have here is a binomial, which means two terms, bi meaning two. So we have a binomial times a binomial. And what we have to do is the same thing we would do if we were multiplying two binomials in the real number system, is we're going to FOIL, which simply means I'm going to multiply the first terms. So let's see here. 1 times negative 3 is negative 3. I'm going to multiply the outer terms, and 1 times 2i is 2i. I'm going to multiply the inner terms. Negative 3i times negative 3. Negative times a negative is a positive, so I get 9i. And then the last terms, negative 3i times positive 2i is negative 6i squared. All right, now I'm going to collect like terms. So I get negative 3. Looks like I've got a 2i and a 9i, which gets me 11i. And then this minus 6i squared is like having plus negative 6i squared. Now remember, let's put this off to the side here. Let's just recall that on the previous slide we said that I squared is equal to negative 1, didn't we? So if we have something like negative 6i squared, that is the same thing as negative 6 times negative 1, which is simply going to be 6. Okay, so this whole piece here turns into 6. And now I see that I can add the real parts, which were the negative 3 and the 6. And so negative 3 plus 6 is 3. And I'm going to hook on that plus 11i. And that's what the product of z and w is. Now let's look at how we might graph a complex number. Now remember that a complex number contained two parts, didn't it? We had that z equals a plus bi. So we have the a and the b, the two parts. And because we have the two parts, we can actually use the rectangular axes that we're used to, where the horizontal axis represents the real component, and we can see that in this fractal image, that horizontal axis represents the real axis or the real part of the complex number, and the vertical represents the imaginary part or the imaginary axis. Complex numbers in the form of z equals a plus bi then can be represented by the ordered pair a comma b on the complex plane. Now this complex plane looks like the rectangular coordinate plane that we talked about up here. The only difference is that we are representing those axes different. So that horizontal axis, like we talked about in the fractal image, instead of having x, we might call that the real part. And instead of having y, we would call that the imaginary part. And when I say imaginary part, what I mean is axes, right? A is going to represent the coordinates for that horizontal axis, and B represents the coordinates for the vertical. So this complex number, z equals a plus bi, is represented by the ordered pair a comma b. All right, on the next slide, let's take a look at some examples of that. Let's look at an example. Graph the complex numbers z equals 1 minus 3i and w equals negative 3 plus 2i on the complex plane. So to indicate that this graph is a complex plane, I'm going to make sure that I identify what the axes are. We know that the horizontal axis represents the real axis, and we know that the vertical represents the imaginary axis. If we don't label these, running out of room there, if we don't label these, then it may be difficult to determine what number system we're working in. So by labeling them real and imaginary, it makes it crystal clear. All right, so we want to graph first z equals 1 minus 3i. Remember that 1 minus 3i is the same thing as 1 plus negative 3i. And also, we learned on the previous slide that what that means is that we can plot this complex number simply by identifying what the real part is and what the imaginary part is. So starting at the origin, I'm going to move to the right 1 unit, and then I'm going to move down 1 and 2 and 3. And this point right here represents the complex number z equals 1 minus 3i. And that is because it has the ordered pair of 1 comma negative 3. All right, now let's take a look at w. W is equal to negative 3 plus 2i. So along the real axis, we're going to go to the left, 1, 2, and 3. And then on the imaginary axis, we're going to go up 1 and 2, landing us in the second quadrant. So this point in the second quadrant is the complex number w, and it's represented by the ordered pair negative 3, comma 2.